Hello everyone, I am Dr. Gargi, an assistant professor of Brainware University, and today we're gonna discuss about the NMR, that means nuclear magnetic resonance spectroscopy. So before going to the details, first we need to understand about the spectroscopy. What is spectroscopy? The spectroscopy is nothing but a scientific technique which is used to the study between the study the interaction between the matters and the electromagnetic radiation. That means what? When the electromagnetic radiation, that means simply light, when it falls on any object, what will happen? The atoms or molecules, they will absorb that energy, some amount of energy they will absorb, and the rest of the energy that will be transmitted. So the how much energy is absorbing and how much energy is transmitting, this all interaction and all the details will get from the spectroscopy, and accordingly we'll get a spectra. For an example here, it is an prism, a white prism. The white light, the light beam is falling on that prism. So the atoms, or that they will get excited, they will absorb the energy from that light, and the rest of the light that will be transmitted according their wavelength, so, and will get a spectra with the 7 colors. This prism experiment we all know. It is a very basic of the spectra, right? Okay. So now slowly we are going in details of the NMR. So in the NMR, the name is nuclear magnetic resonance spectroscopy. Nuclear. So that nuclear, the name is coming from the nucleus. So that's why we have to understand the basic structure of atom, because the nucleus that is only present in the atom, right? So how the structure look like? The atomic structure, this is the very basics of atomic structure, where the nucleus, it is consisting of two subparticles, the fundamental particles mainly. One is proton, another one is neutron, right? Proton is positively charged, neutron is neutral. This is the basics of the nucleus of any atom. And around this nucleus, the electrons are revolving in a particular orbit. This structure we all know. So the nucleus is revolving, but the nucleus, this is not at all in rest. It is also spinning, or it is also revolving. It may spin in clockwise or anti-clockwise in two directions. So that this spin or the state of that spin, that can be defined by this spin angular momentum, spin quantum number. Spin angular quantum number, it is denoted by capital I. Okay, so this much only we have to remember, that the nucleus spin quantum number is I. Okay, nucleus is spinning, either it is clockwise or anti-clockwise. It has also its direction, so that's why it is a vector. Okay, how does the NMR work? We got an idea from the previous slide that the the atoms has the nucleus, and the nucleus has its own spin. It may be clockwise or anti-clockwise. So in any object, the atoms are inside the atoms, the nucleus are revolving, the nucleus are spinning. So they can spin in any direction, means they are spinning in clockwise or anti-clockwise, but it can be in any direction. Like here, these red balls are basically the nucleus of atom. So the nucleus are revolving without any external magnetic field. That means in free cases, in normal cases, they are spinning in any direction. Now if the sample, if we inject inside the magnetic field, what will happen? The direction will be aligned with that magnetic field. Now, if we give the radio frequency, that means electromagnetic radiation, like the spectrum in the first slide, we have shown you that the electromagnetic radiation or the light is falling on any matter or any object. Here also, the electromagnetic, now the atoms or the nucleus are under the magnetic field, but no radio frequency, no external energy is given. Now, from the light source, if we are give if we give the radio frequency, the electromagnetic radiations, what will happen? The nucleus, they will absorb some amount of energy. They are slowly absorbing this energy, and at a particular time they will go to the higher energy level when they will absorb a particular certain amount of energy. And now, if we switch off that energy source, the radio frequency, what will happen? They will liberate, they will eliminate the external, the energy, the excess energy, and they will go to the ground state. And that amount of energy, how much they have eliminate, or they have remove the excess energy, that will be detected by the NMR detector. So this is the very basic principles of NMR. Now, who will give the NMR? All are all molecules NMR active? So this is the answer. The I, the spin angular quantum number, the spin quantum number or spin angular quantum number, I, capital I. If it is zero, then that atom or that molecules will be NMR inactive. For an example, here the helium, carbon, oxygen, sulfur. If you see this mass number, all are divided by 4. So if the mass number is divided by 4 or can be divided by 4, then it will be NMR inactive. Rest of the atoms are NMR active. That means the mass number which is divided by 4, which can be divided by 4, they are NMR inactive. They will not show any NMR spectra. But others, rest of these atoms, others will show the NMR spectra. So this is the NMR spectra. Here you can see the 5 lines are there, right? 5 lines. That means 5 different types of protons are present in one compound. Now you can see here one delta ppm that is written. What is that? It is the chemical shift. Chemical shift tells you the type of protons. The carbon or the carbon. In the carbon NMR, it will show the carbon. In the proton NMR, it will show the proton, the types of proton. Now integration. Integration means the sigmoidal curve. You can see the each peak or each lines, they are consisting of one sigmoidal curve. This is the integration. That means the area under that peak. So it tells you how many protons are there. The area, that gives you the number of protons, the number of uh, chemically equivalent protons. Okay, and the splitting, if you see that the lines, the 5 lines, they are not a single line. Only one, this one is single line, but this line, these are not a single line. They looks like one single peak, but it is also splitted to different other lines. Okay, so this is the splitting, and it tells about the neighboring proton. That means the protons we are talking, suppose Hc, we are talking about Hc. So the neighboring proton is Hd, this one, this Hc, the neighboring proton is Hd. So how many neighboring protons are present there, that will be told by the splitting or the multiply. Slowly we'll describe more about this NMR spectra. So now you just have a look how does NMR spectra looks like. This is a some lines are there, and the one line may be splitted to several lines, and the chemical shift delta, that unit is ppm, okay, parts per million. Now interpretation of the NMR spectra. Number of signals. In the previous slide only I told you that the signals, how many signals, this peak, one peak, these are not peak, these are signals. In the NMR we used to call all the peak as a signal. So how many signals we are getting, that depends on the number of chemical equivalent protons. Okay. For an example here, methyl alcohol CH3OH. So there are two different type of proton. Type means the chemical equivalent protons or magnetical equivalent protons. Chemical equivalent protons means the number of protons which are experience the same chemical environment or electronic environment. That suppose this CH3, the three hydrogen. Suppose this three CH3 three hydrogen. These three hydrogen atoms are all in the same type. So they are in a same group. But OH hydrogen, it is not at all same like CH3. So it is another type of proton. So two protons, two different type of protons are there. So if we want the NMR spectra of methyl alcohol, from that structure only we can imagine that we'll get two peaks, right? Two signals. Because from the structure only we have the idea that it will show two different protons, two different type of protons, so two different type of signals will get. For an example, ethylamine, see, CH3 CH2 NH2. So anyone can tell that there are three different type of protons, three different chemically equivalent protons, because this CH3, all the hydrogens, they are experience the same environment, chemical environment. CH2, these two hydrogens are also experience the same chemical environment, because this CH2, it is attached with CH3 and NH2. Both the hydrogens are the similar distance with this NH2 and CH3, right? Similar like NH2, here also the two hydrogens, they are experience the same chemical environment or electronic environment, whatever. So likewise, we have to first identify how much chemically equivalent or how many chemically equivalent protons are present in our compound. Then only that many signals will get. So before interpret any NMR spectra, first we need to understand several things. First is the chemical shift. Already I have discussed in previous slide. So what is that? The chemical shift is the position of an NMR, is the position of an NMR resonance. It is measured in parts per million, and it is the position that is relative to the reference compound, and this compound is typically tetramethylsilane, TMS. That means what? Chemical shift that will give you the position of the signals, that will give you the positions of the signal with reference, with respect to the reference. This is the reference 0. Reference means the 0 ppm. Okay, and this reference we are getting from TMS, tetramethylsilane, is very important for your exam. Okay, and shielding, deshielding. What is shielding? What is deshielding? Shielding means shield. Shield means what? The nucleus. It is now under external magnetic field. So it is experience more magnetic field. Now, if we can shield it with the electron cloud, then some amount of external magnetic field it will experience less. That is called shielding. So, to be clear, the nucleus in the atom, there is nucleus, but not the nucleus is present, not only the nucleus is present in the atom. Around this nucleus, the electrons are also revolving. So the nucleus that is experience magnetic field, that we are assuming that there is no electrons. That we are assuming only nucleus directly experiencing magnetic field, the external magnetic field. But in practical, what is happening? External magnet, in between the external magnetic field and the nucleus, in between that the electrons are revolving, and their direction is just opposite to the external magnetic field. So the electrons around this nucleus, they are basically making an induced magnetic field, and it is opposing, it is reducing the external magnetic field which the nucleus is experiencing. So what is basically happening? What is basically happening? The nucleus, it is experience less external magnetic field due to presence of electrons. Got it? So now, if in a compound, if the protons which we are talking, so that the neighboring group, if such a group which is uh, extracting that electron cloud, the bonding electrons, if it is attracting towards itself, that means what? The nucleus, the nucleus that is experience more external magnetic field. If the opposite case, that means the neighboring group which is giving extra electrons to that nucleus, that means the plus I effect or the plus R effect, if the neighboring group is showing, that means that nucleus is experience more electrons around itself, so it will experience less external magnetic field, so it will be shielded, it will be more shielded. More shielding means less magnetic field. More shielding means less magnetic field. So show it will show its position towards 0. And the protons which is experience less shielding, that means it is deshielded. So it will experience more in external magnetic field, and it will show higher chemical shift. That means higher ppm. And the shielding protons, they will show the lower ppm. So tell me, there are 4 peaks, right? So which one is shielded and which one is deshielded? We can easily explain that one, right? The first peak, it is near to 0, or it is showing the lower chemical shift, so it is more shielded, it is most shielded here. And the last one, it is showing the higher chemical shift, so it is most deshielded protons. So which one in this compound will experience shielded or deshielded? Will experience more external magnetic field or less external magnetic field? Suppose this proton here, the 2 protons are there, so its neighboring atom is oxygen, which is more electronegative atom, right? More electronegative atom means what? it will attract the bonding electron towards itself. The bonding electron, it is attracting towards itself. That means this proton, they are experience less electrons around itself, so it will experience more magnetic field. So these two protons are deshielded, the most deshielded protons. This peak, the last peak, it is due to these two hydrogen, two protons. And the most shielded proton will be obviously which is far away from the oxygen or OH, this one here. The three protons are there, CH3, this is the CH3 group. So these three hydrogen, it is far away from oxygen, so it is experience more electron cloud around it, so it will be most shielded. That's why the first peak, it is due to the CH3, the terminal CH3. Got it? Okay. Now, I have told before that TMS, the tetramethylsilane, has been used as a reference, 0. This question is very important for your exam, okay? So please understand it carefully. Tetramethylsilane, this is the chemical structure, tetramethylsilane. In the center silicon and 4 CH3 group are attached with that. You can see that all the CH3 groups, these are all same, the same chemical equivalent. You can see all the CH3s, these are all same. So they will show only one single peak, and it is most upfielded, it is more shielded. That's why it is taking as 0 ppm. No other compound has been shown this much shielded proton. So it is considering as 0 ppm, and the other criteria is also present, like it is chemically inert. If the reference we are taking which is chemical reactive, and that reference when we are taking with the compound, with our sample, if it reacts with that compound, then I will not get my desired peak, will get some other peak after the reaction. So we have to choose the reference which will be which will show the single peak, and it will be chemically inert. So this tetramethylsilane, it is chemically inert, and as there are all the CH3 are same, so it will, and the neighboring atom, this is the silicon, it is not attached with any proton, so they will show singlet, one single peak. And here there are 12 protons. So due to this higher number of protons, it will show a very sharp, very intense peak. So we can easily detect this TMS in the NMR spectra. If we show a very small peak at 0, then obviously it can be omitted. So that's why several criteria are there for choosing TMS as a reference. I hope you all understand. So now this is an example of NMR spectra. So how many types of protons are there? Obviously two types, CH2 and CH3. So CH2, it is denoted as A, and CH3 protons, these are denoted B. CH3, all the three protons are chemically equivalent, so they all are same. CH2, this is also chemically equivalent. The two protons, these are chemically equivalent. So these two protons, these two protons are denoted as A. Okay. Now you have to tell which one is deshielded and which one is shielded. This CH2, if you see, this is attached with the bromine. Bromine is electronegative atom. So the so the protons, if it is near to the electronegative atom, obviously it will experience more magnetic field. That means it will be de-shielded, because these bonding electrons, it is attracted towards bromine. Bromine is taking all the electrons towards itself, the electron clouds. So there is very less electron cloud present to protect that nucleus, right? So that's why it is experiencing more magnetic field, and it will show higher chemical shift here. And this CH3, it is one carbon atom far away from bromine, so it will experience less external magnetic field. Yes, it is experience less magnetic field, and it will be shielded here. So we'll get two signals. One will due to A protons, and one will due to B protons, right? B will be more shielded and D will be de-shielded. Okay, I think this much you can understand. Now, splitting, or the splitting multiplicity. As we have seen in previous slide that the signals peak, not peak, whatever I have told peak, this is not actually peak. In NMR, this peak are used to call as a signal. Okay, so all the signals are actually not a single peak. These are consisting of several other small lines, right? Not a single line, small line. Which one? Some signal shows one single, some signal shows two line, some signal shows three lines. So how this splitting is occurring, that depends on the splitting multiplicity, and actually it depends on the neighboring proton. Okay, if there are two chemically equivalent neighboring protons are there, so we'll get n plus 1, that means 3. 2 plus 1, 3 peaks will get. 3 peaks, that means triplet. So we'll get 3 lines. So if we get only one single line, it will be singlet, no equivalent neighboring protons. If we get duplet or doublet, that means one equivalent neighboring protons are there. If triplet, that means two, always one will be added. If we get quadruplet, that means 4 lines, then 3 equivalent neighboring protons will be present. Likewise, it will increase. Okay, and these are the intensities. 1, then 1 is to 1, that means that 2 lines, if we get 2 lines, the intensity will be same, the 2 lines height will be same. 1 is to 2 is to 1, that means one line and the next line will be just double intensity, and then again 1, that means again half. 1 is to 2 is to 1. 1 is to 3 is to 1 means 1, 3 times more. 1 is to 3 is to 3, and then 1. Likewise, okay. Likewise, the intensity will change. So it only, the splitting multiplicity is depends on totally the neighboring protons. The neighboring protons, if 1, then 1 will be added. That means n plus 1. If n number of neighboring protons are there, then obviously we'll get n plus 1 number of signals or lines, sorry, n plus 1 number of lines in a single signals. Okay. This is an example of NMR spectra. I think you all can interpret this NMR spectra now. So this is an example of ethanol, CH3CH2OH. So in the structure CH3CH2OH, you can see there are 3 types of protons. This CH3, they belongs to one type, CH2, that belongs to one type, and OH, this hydrogen is belongs to another type. So there are 3 types. That's why we got 3 types of protons. Now Which one will be deshielded? Obviously, the hydrogen which is attached to oxygen, it will experience more chemical shift, or it will experience more magnetic field, so that's why it will be deshielded here. Next will be obviously CH2, because it is this CH2, it is attached to one carbon further, one carbon far away from oxygen, so it is near to the oxygen. So this CH2, it belongs to the, this peak is belongs to the CH2 because of oxygen. Now the CH3, it is far away from oxygen. 1 2 3 1 2 3 3 bonds away, 3 bonds away from oxygen, so that's why it is most shielded, and this peak, it belongs to the terminal CH3. Okay, now splitting, which one will show doublet, which one will show triplet? First, see the CH3. I told you the splitting will depends on the neighboring proton. So neighboring, how many protons are there? 2. 2 because of CH2. So we'll get triplet CH3. See, 1. That's why it shows triplet. 1, 2, and this one 3. Triplet. Next, CH2. It's shown 3 neighboring protons of CH3, right? And 1 neighboring proton of oxygen OH. But this oxygen OH is generally is not considered, because this oxygen hydrogen, it is very sharp or very strong chemical exchange. It shows very rapid chemical exchange. So that's why this hydrogen will not be detected by the NMR. So only we'll consider the CH3 protons. So there are 3 hydrogens, so we'll get quartet. That's why quartet means 4 signals. Here also we see 3 plus 1 4, so we'll get 4. Okay, now this OH hydrogen. As I told, this hydrogen, the OH hydrogen that experience chemical exchange with the solvents, whatever the solvent or we are taking, they experience the chemical exchange with that solvent proton, and it is very rapid to identify or to detect by the NMR. So that's why this hydrogen cannot be detected by the NMR instrument. So that's why this hydrogen will couple with the neighboring proton. That's why it is considering as a proton with the 0 neighboring proton. So if the hydrogen, if there is no neighboring protons are there, so what will happen? It will show one single peak, that means singlet. That's why this OH will show singlet, one signal. Okay, this much is the interpretation of NMR spectra, very basics of NMR spectra. But what is the application of that? Basically, we get an idea from the NMR spectroscopy or NMR spectra, or the chemical structure. In our research, we generally do the NMR spectra for getting the chemical structure of our compound, of our sample. What is the chemical structure? And how many protons are there? How many type of protons are there in the compound? That also we can get idea from the NMR spectroscopy. In the medical field also, this NMR spectroscopy can be used. By NMR instrument can be used, like MRI. MRI we all know, right? Is a non-invasive diagnostic tool based on the NMR principle. And also for diagnosis of different organs, tissues, and different other cases. Okay, but in chemistry, in research, we generally use NMR spectra for getting the chemical structure, for getting the types of protons and how many protons are there from the area or the integral part of that. We get an idea of how many protons are there in a single, how many types of protons are there in that compound. Okay, so these are all from my side about the NMR spectroscopy in very short description. I hope you all understand all these things, and please try at home to solve all the questions regarding NMR spectroscopy and let me know. Okay, thank you.